Hi guys, in this video we're going to continue our exploration of what we call mathematical correlation, or the connectedness between, say, two variables. That is, like, number of hours I study on a test and the score I get, or, say, number of hours after it rains and the relative humidity in the air after a certain amount of time. But basically, variables that are connected to one another, but there's not an exact rule or pattern between them that tells you, if you know one, what the other one would be. So we tend to observe data that occur, a lot of the times in a linear fashion or in a line-like fashion, to see if we can kind of pick up on a pattern to predict values that were not in the original data set. So, for example, we'll get into the method for finding equations of best fit lines here in a second. But let's say I had a scatter plot, and we look at the scatter plot here. We notice that as x is increasing, y tends to decrease. So this would be a good example of we would say there's a connection between these two variables, x and y, but good example of what we call a negative correlation, because as one is going up, the other one's going down. What we want to do is be able to describe the data beyond the data set, and there's a method for doing this. And of course, we've been exploring that, and that's using best fit lines. Okay, so here's the deal. We're gonna find the equation of a line of best fit, or best fit line, and in the last video we kind of outlined this process here for doing so. So we're going to go ahead and get started by saying, okay, now recall that we're going to be using point slope form of a line. So y minus y1 equals m times x minus x1. As far as this process for finding the equation of this line goes, the easy part are these first two steps over here. Make your scatter plot and sketch your best fit line. Okay, so we've already got a scatter plot here. We're going to go back to our data set, and you can see these points up over here on the left, but we're going to start by saying, okay, so we would have graphed these points. You notice that I have decimal values in here, and there's nothing wrong with that. But let's go ahead and make our line of best fit. Okay, line of best fit. So to the best of my ability, I'm going to try to fit a line to this data set that kind of describes the pattern going on. Recall that you don't necessarily have to have your line connecting your first and last dot. I mean, if we did that here, it would look like this, and you notice, that wouldn't be too bad, but you want to split the data right in half. And I'd say, well, I kind of like this line maybe a little bit better. I mean, that's not a horrible looking line that we've drawn here. So if this is my line of best fit, we're already done with steps 1 and 2. Make my scatter plot, sketch my line of best fit. Now step 3, we need to choose 2 points that are very, very nearly on this line of best fit. So we're going to look at this entire line of best fit, and I'll get the 2 points I used to make the line out of the way here. But we have points A through J here. We just need to find 2 points that we say, look like they're really, really close to being on the line, and recall that they don't have to be elements or members of the original data set. So with just my eyes here, this one sticks out to me right here. It looks like the point 6, we trace this over here, 6, 5. So 6, 5 really looks like it's on my line of best fit. And honestly, I know I said that it didn't have to be a member of the original data set, but this point B right here almost looks like it's on my line of best fit. So that is the point over 2, up 8. So we have 2 points, 2, 8, 2, 8, and we said 6, 5. So let's go back and write these points down so that we don't lose them. Put them in our pocket. We say 2, 8, 2, 8, and 6, 5. So now we want to come up with the equation of the line that passes through these 2 points. And according to our point slope form, all we need is a point, of which we have 2. We have 2 points. We got to choose which one we get to use. And also, we need a slope. We need an m. Right now, we don't currently have a slope. So we can sketch these 2 points and plot them and just count rise over run. But you notice in this case, we said we have a negative correlation. That is, if you were to observe the slope of this line from left to right, it's falling. So when we find the slope of this, using our slope formula, we say m equals y2 minus y1 over x2 minus x1. We should get a negative value for slope. So let's go ahead and say, so y2 was 5, y1 was 8. 5 minus 8, there's our negative value. And we say, okay, so now x2 minus x1, 6, positive 6 minus positive 2. So we turn out this slope of negative 3 over, it looks like 6 minus 2 is 4. Negative 3/4. That is, it goes down 3 over 4. And we could kind of verify this by looking at the graph. From the point B to the point 6, 5, which I haven't plotted, it goes down 1, 2, 3, and right 1, 2, 3, 4. So that's roughly the slope of this line. That's all we need, is roughly the slope of this line. So now that we have the slope, booyah, Grandma, we say, okay, so we found the slope between our 2 points. Find the slope between the 2 points, excuse me. Now we want to choose one of the 2 points that we originally started with. And so we started with 6, 5 was on the line. We also had 2, 8. Of these two values, I guess I'm kind of partial to 2, 8. 2 is a little bit easier to deal with than say a 6 and a 5. And 2 and 8, I know this. When I plug in my slope up here, I'm going to have to distribute it through and take it times x1, and my x1 in this case is 2, and that's going to react really well with this denominator here. So we'll kind of take a look at that. So let's go ahead and write out our point slope form of this line. So we have y minus y1 equals slope value times x minus x1. So using this first point and our slope of -3/4, let's go ahead and put our slope in first. -3/4 was the slope. The x value of our point was 2. The y value of our point was 8. And keep in mind, again, it doesn't matter. We could have used the 6 and the 5, and we're going to get the same equation of the line. So going ahead, we'll go ahead and distribute our -3/4, and we get this on the right. -3/4 x. Now a negative times a negative here is a positive. 2 times 3/4 would be 6/4, which reduces, but we say, okay, remember I said that 2 is going to react well with this 4 here. This is going to become a 2, this will become a 1. So we say -3 times 1, -1 would be +3, and then 2 times 1 is 2. And again, you could have gotten +6/4, but notice that's the same thing as 3/2. And on the left here we have y minus 8. So now we just need to get y by itself, isolate the y by adding 8 to both sides here. We're going to have to do some fractional addition. So we say -3/4 x, so there's our slope, +8 plus 3/2. We can do some scratch work on this. 8 plus 3/2 is the same thing as 8 wholes plus 3/2. We can make this into a 2 down here, but we also have to double the top. So we get 16/2 is the same as 8, plus the 3/2 that we're adding it to is a total of 19/2. And just for my decimal peeps out there, that's roughly 9.5. We're not going to use that, but we say, okay, so plus 19/2. So now, you should always check the feasibility of your answers. Is this feasible? -3/4 x plus 19/2. So we're going to go back over here and we'll type this in. So we say y equals -3/4 x plus 19/2 and hit enter. You'll notice that it's very, very close to our line of best fit. It's not going to be perfect, but it's a good approximation. So now let's say I wanted to go beyond my data set. And we use this word extrapolation to describe what I'm talking about here. But what if I wanted to know where would my data have been if, say, x was 10? Okay, so taking our very first line of best fit out of there, which was this guy, this is the equation, the graph of the equation of the line of best fit we just found, that -3/4 x plus 19/2. If we were to say at 10, it looks like it would be around a height of 2, and that's basically just saying if the data had continued out to an x value of 10, then it probably would have been somewhere around 2, because remember, this line basically describes what your data was doing in the first place. So now we'll take an x value of 10, we'll plug it into this equation we have right here. Okay, plug it in. So let's do it. We get y equals -3/4 blank plus 19/2. And if we were to put a 10 right here, okay, this 10, we could put a 10 over 1 and say, well, 2 goes into 4 twice, 2 goes into 10 5 times, and so now we have -3 times a +15, a +5, excuse me, that's -15, and then 2 times 1 on bottom, so -15/2 plus 19/2. What do you know? We end up with 4/2, which is the same thing as 2. So basically we're saying, hey, look, if the data were to continue in this fashion, it probably would have been somewhere around 2 when we got to an x value of 10. So now, that was just another example of how you would find the equation of a best fit line. I do want to take the time, however, to look at this graph right here. I did plot these points up here on the left, and we say, okay, so looking for a correlation. Remember, correlation means just a connection between things, and if I were to say, is there a connection between my two data sets here, x and y? And you notice as x is getting bigger and bigger and bigger, your y values are just kind of all over the place. It looks like somebody fired a shotgun at this. But I'll tell you what, there's really no connection between these data points. So we'd say this would be a very good example of a data set which has relatively no correlation. And just to kind of illustrate that here, you could say, well, my data is neither kind of going up or down. I mean, you could try to pass a line of best fit through this, and you wouldn't have a whole lot of luck. I mean, because really any line that you use would split the data set, and there's no real pattern between them. So this would be an example of what we say is a data set that has relatively no correlation whatsoever. So if anybody ever asks you to find a line of best fit, you just basically come back with, well, I can't, because no line really describes what's going on with the trend in this data.